So here we need to show that x raised to the power of 2n plus 1, that's given by 2x raised to the power of n cosine of n theta, whenever we have this quadratic equation in x, which is x squared minus 2x cosine theta plus 1 equals to 0. So let's begin with our quadratic equation. So here we have x squared minus 2 times cosine of theta multiplied to x plus 1 equals to 0. So this is a given equation. This is a quadratic equation. So we can use the standard formula for finding out the roots of a quadratic equation, and that should give us x equals to, so we have negative of the coefficient of x, which is negative 2 cosine theta, plus or minus, since this is a quadratic equation, we'll have two roots. We have square root of the coefficient of x, which is negative 2 cosine theta. We'll square it, then we'll subtract from it 4 times the coefficient of x squared, which is 1, and the constant, which is 1. Whole thing divided by 2 times the coefficient of x squared, which is simply 1. So we now have 2 times cosine of theta plus or minus, so within the square root we'll have 4 times cosine squared theta minus 4 divided by 2, which will be 2 times cosine of theta plus or minus. So what we'll do, inside the square root we'll take negative 4 as the common factor, so we'll have 1 minus cosine squared theta whole divided by 2. This gives us 2 times cosine of theta plus or minus. So negative 4 can be also expressed as 4 times I squared. So here we're using the fact that iota squared is negative 1. This is true by definition. And we know that sine squared theta plus cosine squared theta. So this is an identity with a value of 1, which would mean that 1 minus cosine squared theta will be equals to sine squared theta. So we will now have 4i squared times sine squared theta whole divided by 2, which gives us 2 times cosine of theta plus or minus. So for the square root of 4i squared sine squared theta will be 2i sine theta divided by 2. So we can factor out 2 from both the numerator and the denominator, which leaves us with cosine of theta plus or minus iota times sine theta. So this is the value of x. Now what we'll do, we'll raise both sides to the power of n. So we have cosine of theta plus or minus iota times sine of theta whole raised to the power of n. Now here we can apply the de Moivre's theorem, which states that whenever we have cosine of theta plus iota times sine of theta whole raised to the power of n, so that's equivalent to cosine of n theta plus iota times sine of n theta. Fine. That means we can rewrite our expression as cosine of n theta. So here we have plus or minus, that's fine. We're going to also consider the negative value. So we have iota times sine of n theta. We're going to label this as number 1 and number 2. This is x raised to the power of n. And again, using equation number 1, if we raise both sides to the power of 2 as well, we're squaring both sides. So that means x raised to the power of 2n will become equals to cosine of theta plus minus iota times sine of theta raised to the power of 2n, which becomes equals to cosine of 2n theta plus or minus iota times sine of 2n theta. So this is x raised to the power of 2n. In the next step, we're going to add 1 to both sides. This will be equals to 1 plus cosine of 2n theta plus or minus iota times sine of 2n theta. Now we are going to use some trig identities. We know that 1 plus cosine of theta, this is equals to 2 times cosine squared theta over 2. And if we substitute the value of theta with 2n theta, so that means we'll have 1 plus cosine of 2n theta. This will be equals to 2 times cosine squared. So we have 2n theta over 2. This will be simply n theta. Fine. And we have sine of 2n theta. So when we expand this, this will be 2 times sine of n theta multiplied to cosine of n theta. So we'll use these two values to rewrite our given expression. The 1 plus cosine of 2n theta will become 2 times cosine squared of n theta plus or minus iota times, so we have sine of 2n theta, so this will be 2 times sine of n theta times cosine of n theta. Fine. So this is going to give us the value. So we'll take 2 times cosine of n theta as the common factor. All will get multiplied to cosine of n theta plus iota times sine of n theta. Fine. So this is the value for 1 plus x raised to the power of 2n. Now here we have already obtained this value. So if we look at equation number 2, we can replace this value with x raised to the power of n. So we have 2 times cosine of n theta multiplied to x raised to the power of n. Therefore, we have successfully shown that 1 plus x raised to the power of 2n, this is equals to 2 times x raised to the power of n times cosine of n theta whenever we have our expression given by x squared minus 2x cosine theta plus 1 equals to 0. Hence proved.